Good morning. Welcome to Mission Control Houston. As I promised, we have here with us Dr. Christian Otto, who's the principal investigator for the Ocular Health experiment, which flight engineers Rick Mastracchio and is helping Mike Hopkins with today. And he's going to tell us a little bit about what's been going on with that experiment, what it's about, and what some of the results they've started seeing are. Thanks so much for joining us.
Yeah, thanks, Brandi. As you may know, the Ocular Health experiment was instituted because of the eye problems that were documented in a number of crew members. As you may know, up to 50% of crew members have changes in their vision following their space flight. In 2005, we found a rather concerning eye problem, which is swelling of the back of the optic nerve as it enters the eye. And this is actually quite a serious problem. In fact, we see it in many diseases such as glaucoma and head trauma. It can be a sign of elevated intracranial pressure. And if this does not resolve, it can actually lead to blindness. And after some investigation, there's actually been 6 crew members now who've developed this serious finding. That there have been other findings as well, such as changes in the structure of the eyeball itself. It's been somewhat compressed in many crew members, and also widening of the covering of the optic nerve behind the eye. And both of these findings are actually suggestive of elevated intracranial pressure. So this is of concern to the program, particularly with future longer duration missions.
That makes sense. Do you have any theories about what's causing it or why we're seeing that?
Yeah, that's a very good question. And one of the leading hypotheses is the cephalad fluid shift. So this is here on Earth, we have gravity acting on our fluids. Fluid is drawn towards the lower part of the body, but in space flight, it actually gravitates more towards the head. As you see here in the video that we're showing, you can see that fluid tends to move upwards in weightlessness, and one of our concerns is that this may lead to elevated intracranial pressure. And you can see that fluid around the brain actually communicates with the back of the eye through around the optic nerve, which is also surrounded by the sheath. As you can see this with the blue arrows. And if the pressure increases, it can actually widen the back of the optic nerve sheath and push on the eyeball. And this is why we see this compression of the eye, as you can see here. And these pressure differentials can cause changes in vision. And we can measure vision by refractive change or diopters. This has to do with the optical power of the eye. And these changes result in degradation of near vision.
Okay, so that's what we think is kind of causing it, I guess. What are the crew members doing on board the space station to help get us more information?
Yeah, so as part of the Ocular Health experiment, we have a number of tests that we're conducting. This is also part of the medical ops data collection as well. But things such that you might get done in your family doctor's office, or if you go and see the optometrist or ophthalmologist, we're doing fundoscopy. Fundoscopy ops are going on today, I believe, with Mike Hopkins and Koichi Wakata, where we're taking pictures of the back of the eye. This is as though you're at the doctor's office and they're looking in the back of your eye with an ophthalmoscope, but this has a much more higher resolution. We can look at the vessels of the eye, the retina, and the optic nerve. We're also doing ocular ultrasound. This allows us to look at the structures of the back of the eye, measure that compression if it's occurring, and the widening. And there's a new device on station now called ocular coherence tomography. It's a very powerful ultrasound device that lets us look in very fine detail at the retina and the optic nerve to see swelling long before we can see it with an ophthalmoscope. So this allows us to more carefully monitor crew members whether they're headed towards these findings. We're also measuring intraocular pressure, so taking a pen-like device, and this taps on the eye, and we can measure the pressure in the eye, because we think the differential between the pressure in the eye and the pressure in the brain may also be a causative factor in this problem.
And this is all stuff that the crew can kind of do amongst themselves without help from the ground, or I guess they get talked through it, but...
Yeah, and that's a great question. And in fact, the crew members are obviously extremely talented and skilled, yet many of these are very sophisticated medical tests. So there's a large team of folks here on the ground, biomedical controllers. We have subject matter experts who actually guide the crew through many of these procedures. So they're sort of the eyes, and the crew are the hands, and they help them through many of these tests to acquire these medical grade images. So it's a team effort.
Okay, and so far are they doing a good job of getting the information for you?
Yeah, in fact, we have data from 2 crew members now, and they've done a wonderful job in collecting this very sophisticated data across many different tests, and this is actually helping us understand this problem much better.
Okay, great. Well, so as you get a better understanding, any ideas? Is it something you're going to be able to prevent, or is it something you just accommodate on longer duration missions?
Yeah, and another great question. So the concern is for longer duration missions. So as you're alluding to, the goal here is to come up with treatments and countermeasures to prevent what we think may be happening. And again, our leading hypothesis is the cephalad fluid shift. So some of the possibilities are mechanical factors that help draw some of that fluid back towards the legs. And the Russians use a device called the bracelet, which is essentially a tourniquet around each thigh. It's calibrated, but that helps keep some of the venous blood in the legs and preventing some of that cephalad fluid shift. That's a potential countermeasure. There's also a negative pressure suit. There's both a US version and a Russian version that is basically like a large set of pants that you put on, creates a negative suction and draws fluid down towards the legs. That might not be a perfect option in the future, but there may be other versions that aren't quite as cumbersome. Other things that we're considering are drug treatments and so on. So the experiment's giving us insight into what countermeasure we might be able to employ.
So will these experiments go on a long time before we start seeing some of the countermeasure type experiments, or is that coming in the near future?
Yeah, and another great question. In fact, following closely on the heels of the Ocular Health experiment is the fluid shifts experiment, another NASA experiment combined with other outside investigators that we're sort of an occupational or observational study to look at what's happening to the crew member. We're not using any interventions to see if we can change what's going on. But the fluid shifts experiment will employ the Russian Chibis suit, which is a negative pressure device. It's actually on board on the Russian segment. So this is an exciting collaborative experiment with our Russian colleagues, and to actually look at these changes and the changes we're seeing in the crew now, can they be reversed using, for example, the Chibis negative pressure suit? So that'll give us a clear indication if that's a viable countermeasure.
Okay, well, I'm sure we'll be hearing more from you about that soon. In the meantime, is this something that could help us here on Earth, or is it just for people who are going to space?
Yeah, and that's another great question. And, with this problem, the visual impairment intracranial pressure problem, we're really on the cutting edge of several areas of clinical and medical science here on the ground. For example, understanding diseases of the eye that involve intraocular pressure and the difference between intraocular and intracranial pressure, such as glaucoma. Better understanding diseases that lead to papal edema. Also diseases that involve circulation of cerebrospinal fluid in the brain, such as idiopathic intracranial hypertension or hydrocephalus. The other exciting thing is the development of new technologies that will play a critical role in medicine on Earth, such as ways to measure intracranial pressure without drilling a hole in someone's skull and putting in a device. This is very exciting with huge implications for, head trauma and neurosurgery and neurology, and also ways to measure diseases of the eye, such as ultrasound, which many of these techniques are being pioneered right here at NASA.
Sounds like it could be good news for a lot of people.
Definitely.
Well, thanks so much for coming and talking with us. We really appreciate it. And
My
like
pleasure.
I said, I'm sure we'll have you back to give us more updates as the experiments go on.
Thank you.